The machining floor of the Rover Company's Solihull factory ran 24 hours a day in the spring of 1942. Overhead, fluorescent lights burned through the night shift. Lathes screamed against hardened steel. And then, one by one, they stopped. Not because of bombing. The Luftwaffe had done its worst to the Midlands already. Not because steel was short, though it was. The lines stopped because the cutting tools were dead, worn to blunt stumps after hours of work that should have taken days. High-speed steel tools, the best Britain's domestic supply chains could reliably provide, were failing against the hardened armor plate and precision engine components that Churchill and Valentine tank production demanded. A tool that should have held its edge for a full shift was lasting 3 hours, sometimes 2. Every blunted tool meant a machine sitting idle. Every idle machine meant a fitter standing at a cold lathe, waiting for a replacement that was increasingly difficult to find. The tools that wouldn't blunt, the tools that German and German-licensed manufacturers had supplied before the war, were made of tungsten carbide, a material so hard it sat second only to diamond. A material whose mass production process had been pioneered, patented, and commercialized almost entirely by German industry. And in 1942, with that supply chain severed completely, Britain was discovering what it meant to fight a mechanized war without the materials that mechanized war required. Tank production targets for 1942 stood at figures the Ministry of Supply was already struggling to meet. The North Africa campaign was consuming armor faster than the factories could replace it. Churchill pressed manufacturers relentlessly. The bottleneck wasn't steel. It wasn't labor. It was a cutting tool problem that nobody in Whitehall had a ready answer for. The answer wouldn't come from the Ministry of Supply. It would come from a company in Manchester that built electrical switchgear. To understand what Britain had lost access to, you have to understand what tungsten carbide actually is and how completely one nation had come to own it. In 1923, a German chemist named Karl Schröder, working at Osram's research laboratory in Berlin, successfully synthesized a stable, manufacturable form of tungsten carbide by binding tungsten carbide powder with cobalt under extreme sintering temperatures. The result was a composite material of extraordinary properties. A Vickers hardness of roughly 1,500 compared to 800 for hardened high-speed steel. A melting point above 2,800 degrees Celsius. The ability to maintain a sharp cutting edge at temperatures that reduced high-speed steel to a softened, useless nub within minutes. Krupp licensed Schröder's process almost immediately, commercialized it under the name Widia, derived from the German Wie Diamant, meaning like diamond, and began supplying it to manufacturers across Europe and beyond from 1926 onward. The patents Krupp held were comprehensive: powder particle size, cobalt binder ratios, sintering temperature curves, grain structure specifications for different cutting applications. Buying into tungsten carbide technology before the war meant buying into Krupp's licensing structure directly or indirectly. General Electric in America had done exactly that, developing their Carbaloy product range under German license. British manufacturers had relied on imported Widia tooling or licensed equivalents. Domestic production capacity for tungsten carbide in Britain was negligible. Nobody had pressed the point because the German supply was reliable, the price was acceptable, and developing an independent capability seemed unnecessary. Then September 1939 arrived. German patents became inaccessible. Imports ceased. The licensing agreements that had quietly structured Britain's precision manufacturing industry for 15 years became worthless overnight. A cutting tool that outperformed high-speed steel by a factor of 5 in both speed and longevity had effectively vanished from British factories. What remained was inferior, and everyone on every machine floor in every tank and aircraft factory in the country knew it. Trafford Park in Manchester was the world's first planned industrial estate. By 1942, it covered nearly 1,200 acres and housed over 200 companies employing more than 75,000 workers. It made things that won wars: tanks, aircraft engines, radar equipment, naval guns. And sitting near its center, in a complex of brick buildings that stretched along Westinghouse Road, was Metro-Vickers Electrical Company. Metro-Vickers, as everyone called it, built turbines, transformers, and heavy switchgear. They made early radar systems for the RAF. They were, by any measure, an electrical engineering company. They had no business solving Britain's cutting tool crisis. Except that Metro-Vickers had something most companies didn't: a serious research laboratory staffed with materials, scientists who had spent the 1930s quietly working on hard metal problems driven by their own precision manufacturing needs. Building turbine components and high-tolerance electrical equipment required machining to standards that pushed ordinary tooling to its limits. The Metro-Vickers research team had been studying hard metal behavior, wear resistance, and powder metallurgy not because anyone told them to, but because their own production lines demanded it. When war came and the cutting tool gap became impossible to ignore, they were the closest thing Britain had to a standing answer. The team that took on the problem worked under conditions that mixed urgency with scarcity. Wartime labs were cold, supply deliveries were unreliable, and the German technical literature that might have shortened the development process was now enemy property. What they had was systematic method, accumulated materials knowledge, and the particular stubbornness that characterizes engineers who understand a problem completely and refuse to accept that it cannot be solved with available resources. They weren't trying to break a German industrial monopoly. They were trying to keep the machines running. The fact that both things turned out to be the same problem was something they worked out along the way. The process of making tungsten carbide begins with powder. Tungsten ore, sourced during the war primarily from Portugal and from Burmese deposits increasingly threatened by Japanese advance, was processed into tungsten powder, then reacted with carbon at high temperatures to form tungsten carbide powder. That powder was then mixed with cobalt, pressed into shape under enormous hydraulic pressure, and sintered in a furnace at temperatures approaching 1,400 degrees Celsius. What emerged was not quite metal and not quite ceramic, but something harder and more heat-resistant than either. The physics were elegant. The engineering variables were brutal. Cobalt content controlled the fundamental trade-off between hardness and toughness. A 4% cobalt binder produced a tool of extreme hardness that could hold a cutting edge at high speeds, but shattered under shock loads. A 12% cobalt content produced a tougher tool that resisted fracture on interrupted cuts against armor plate, but wore faster under sustained high-speed finishing work. Grain size added a second variable. Finer tungsten carbide grains increased hardness, but reduced the material's resistance to the microfractures that propagated under cyclic cutting loads. Getting both variables right simultaneously for specific applications required systematic empirical testing that Krupp had spent years accumulating and patenting. Metro-Vickers had to reconstruct that knowledge from physical first principles, one test cut at a time. What they could not do was copy the German patents directly. What they could do was measure outcomes. A tool insert was ground, mounted, run against a standardized steel workpiece at a fixed cutting speed, and examined under magnification after a set number of passes. Wear patterns revealed what the composition needed. Fracture surfaces revealed what the grain structure was doing. The data accumulated slowly, then faster, as the variables narrowed and the formulations stabilized. By working backwards from what the cutting edge showed under failure, they rebuilt what Krupp had spent a decade constructing from the front. By 1943, the formulations were stable and production was scaling. Metro-Vickers and a small number of associated British hard metal producers were supplying domestically developed tungsten carbide cutting tools to factories that had spent the previous year watching high-speed steel wear itself to nothing against hardened steel. The difference was not marginal. It was transformative. A high-speed steel tool cutting hardened armor plate at 30 feet per minute would last roughly 2 hours before requiring replacement or regrinding. A tungsten carbide insert running the same material at 90 feet per minute, 3 times the cutting speed, would last a full shift. The arithmetic compounded across every lathe, every milling machine, every boring bar on every factory floor. Machines that had been idle a third of each shift, waiting for tool changes, were now cutting continuously. The productive capacity of existing machine tools, without adding a single new lathe or hiring a single additional worker, increased substantially simply because the tools stayed sharp. Churchill tank production, which had been plagued by manufacturing delays and quality inconsistencies through 1941 and into 1942, began recovering. The Rolls-Royce Merlin engine, which powered the Spitfire, the Hurricane, the Lancaster, and the Mosquito, required precision carbide tooling for cylinder block machining and crankshaft finishing to tolerances measured in thousandths of an inch. Every Merlin that climbed over occupied Europe carried within it the solved problem of a Manchester research laboratory. Estimates of Merlin production by war's end exceeded 160,000 engines, each one touched by tooling that, 2 years earlier, Britain could not reliably make. There were no photographs of this victory, no operational code names, no dispatches from the front, just machines running longer, parts coming off cleaner, production targets met on floors where they had been missed the month before. Every tool that held its edge meant one more component finished. Every component finished meant one more vehicle completed. Every vehicle completed meant one more crew with the equipment they needed to fight. The war ended, and the German patents became accessible again. Krupp's Whittier documentation, accumulated over 15 years of systematic development, was now open to Allied manufacturers under the terms of post-war industrial reparations. British engineers read through it carefully. In several areas, the formulations Metro-Vickers had arrived at by working backwards from cutting-edge failure patterns matched the Krupp specifications closely. In others, the British wartime development had gone in different directions and arrived at solutions Krupp had not pursued. Crisis had produced not just substitution, but genuine, independent innovation. Metro-Vickers itself did not remain independent long enough to capitalize on what it had built. The company was absorbed into Associated Electrical Industries in 1949, and AEI itself was swallowed by GEC in 1967. The research laboratory at Trafford Park that had rebuilt tungsten carbide technology from first principles was dispersed into the broader consolidation of British heavy industry that characterized the post-war decades. The names of the individual researchers who solved the cutting tool problem did not survive the institutional mergers that buried the institution they worked for. But the knowledge did not disappear. It seeded a domestic British hard metal industry that fed into the global cutting tool market that exists today. Sandvik in Sweden, Kennametal in America, IMC Group across multiple continents. The competitive plurality of modern tungsten carbide manufacturing traces its existence directly to the wartime scramble that shattered German monopoly control of the technology. No single company owns the process now. No single nation controls the supply. That outcome was not inevitable. It required factories that stopped, problems that seemed insoluble, and engineers in a cold Manchester laboratory who treated both conditions as variables to be adjusted rather than facts to be accepted. The Churchill tanks they helped build are in museums now. The cutting tools that shaped them are gone, consumed entirely in the act of making something that lasted. That is what good tooling does. It gives everything and leaves no trace of itself behind.